Hello everybody, I'm Jiaoyang Li from University of Southern California. Today I'm going to represent our team and Old Driver to present our solution for the 2020 Flatland Challenge. Our team consists of 4 PhD students, including myself, Zhe Chen from Monash University in Australia, Yi Zheng and Shaohong Chen from University of Southern California in the United States. We also have 4 excellent and very supportive advisors, including Daniel Haribo and Peter Starkey from Monash University in Australia, Han Ma from Simon Fraser University in Canada, and Sven Koenig from University of Southern California in the United States. The reason why we have team members from different institutes and different countries is that we are all interested in a very exciting research problem called multi-agent pathfinding, or for short MapPath, and we have been working on this problem together for a few years. So MapPath is a combinatorial problem of finding collision-free paths for a team of agents on a given graph. Although it's an abstract model, people have developed many generalized MapPath problems to narrow the gap between this abstract model and the real-world applications. These include MapPath with task assignment, MapPath with motion planning, MapPath with uncertainty, and online and lifelong MapPaths. If you are interested in this problem, you can find more information at this website. Back to the Flatland Challenge, the problem in the Flatland Challenge is actually very related to the MapPath with uncertainty problem and the online MapPath problem. And actually, in our solution, we already use many methods from this literature. Now let's look at our solution. I will first introduce a basic approach that guarantees to solve the problem without deadlocks. I will then introduce some improved approach that solves the problem faster with better solution quality. In the basic approach, we have 2 components. The first one is prioritize planning, which is a popular multi-agent pathfinding algorithm. It first plans a shortest path for first agent, and then it plans the shortest path for the second agent while avoiding collisions with the first agent. Then it plans the shortest path for the third agent while avoiding collisions with the first 2 agents, and so on. So eventually it will find collision-free paths for all agents. But this is not enough because during execution, agents may have more functions. So if, for example, this is an original plan, and if the light blue agent is delayed by the malfunction, then we will have the deadlock. Therefore, we use minimal communication policy to resolve this issue. MCP keeps the ordering of the agents to visit each location and thus guarantees deadlock-free. For example, in this case, if we keep the ordering for the agent to pass through this intersection, then when the light blue agent is in malfunction, we also have to delay the blue agent, and thus the deadlock is resolved. So combining prioritize planning with MCP, we are already able to solve the Flatland Challenge problem. But we can do it better. We introduce 4 different techniques to improve our basic approach. The first one is about the single-agent path planner. We replace the old spacetime A* with shift interval path planning, or SIP. So in this example, this agent wants to move to location BCD. In the spacetime A*, we have to generate a node at every location at every time step in order to avoid collisions with paths of other agents. But in SIP, it compresses a node at the same locations into some time intervals so that the agent can stay at any location at any time step inside this time interval. And therefore, SIP will have much fewer nodes than spacetime A*. The second improvement is about log neighborhood search. We use it to improve the solution quality generated by prioritize planning. So after we find a solution, we select a neighborhood, which is a subset of agents, and we plan the paths for them. If the new paths are better, we replace the old paths with the new paths and repeat this procedure. We developed 3 different methods to generate neighborhoods, include a station-based method where we select agents who have the same start station, an intersection-based method where we select the agent who travels through the same intersection, and an agent-based method where we select the agent who has the longest path together with the agent who blocks this agent. The third improvement is about to handle malfunctions more effectively. Previously, we have introduced MCP, So in this example, because of MCP, when the yellow agent is delayed, it will also delay these three agents. However, these delays are not necessary, because when the yellow agent is delayed, we can actually let these agents to move through this intersection without deadlocks and without colliding with others. Therefore, we design this partial replanning method where we collect the intersection that the malfunction agent is going to traverse and replan the path of the agents who are going to traverse these intersections after the malfunction agent. The last improvement is about solving very large problems. In Flatland challenge, we could have instance that contains more than 1,000 agents. And running process planning for thousands of agents itself is very time-consuming. Like this figure shows, at the very beginning, the runtime for each agent is very low. But then, after we already plan paths for many agents, the path for the future agents has to avoid collisions with the paths of all previous agents. And therefore, the time for the path planning grows exponentially. So in this instance, eventually we took more than 2,500 seconds to solve the problem. However, if at the very beginning we only plan paths for some of agents, and then let the agents start to move, then for the rest of the agents, we plan their paths during execution. As you can see in the figure, this method takes much less time than the previous method. And the reason is that once the agents start to move, the agents already reach their goal locations and disappear from the map. So there are fewer collisions that we need to consider. Therefore, the path planner part becomes easier. And eventually, in this case, it takes us only 600 seconds to solve the problem. So this table summarizes the method we have just introduced. To show the effectiveness of each improvement method, we run experiments on our local generated instance, and here are the score improvement. To summarize what we have learned from this computation, so all the improvement techniques we developed are about improving solution qualities and reducing runtime. So our group's research often focuses on map-path algorithms that have guarantees. We want to guarantee that the agents always reach their goal locations, and we want to guarantee that we always find optimal or at least suboptimal solutions. These guarantees are nice to have, but in practice, we don't need them. What we really need are good quality solutions for thousands of agents, and we need these solutions very fast. These insights lead us to focus on process planning instead of some optimal algorithms. But on the other hand, the optimal algorithms are not totally useless. We use the solution generated by the optimal solutions to identify the improvement space. So we compare the solutions found by the optimal solutions and the solutions found by the process planning. And that's when we realize that actually replanning small groups of agents can improve the solution quality substantially. And that's why we developed the large neighborhood search method and the partial replanning method. For the runtime, we found that develop very effective profiling method can help us to identify which part of the code is time-consuming and adjust our strategies accordingly. For example, we found that for very large instance, the single-agent path finding becomes very time-consuming, and that's why we replace the spacetime A* with SIP and also develop the lazy planning method. And this ends my talk. Thanks for listening.